In this video, I'll talk about the gamma distribution and through an example. So I like to ride my bike, and above, or in another place, we had the, I get 2 flats, say, every 1,000 miles. Okay, so the number of flats I get in 1,000 miles, we said is Poisson. So number of flats, flat tires on my bicycle. Number of flat tires equals X in 1,000 miles is distributed as Poisson 2. So it's variable. It might have no flats. It might have many flats, although that's unlikely. Then if we let y be the number of miles before first flat, then y is distributed as exponential 2. Same lambda here. So this was lambda, and this is again lambda, so that you can just replace them right over. So y has a PDF that looks something like this. The term looks like e to the negative x, so it looks approximately like this, the PDF. Here's the PDF. Okay. So I had a different question. Let's ask how long before I get starting again. How long before I get 3 flats? Okay, so that's kind of like adding up each of the y's. y1 is distributed as exponential 2, and same for y2 is also another independent exponential 2, and y3 is exponential 2. So if we let z equal y1 plus y2 plus y3, then z is the time that I will get 3 flats. So this is a random variable. It's a function of random variables. These y's are all independent, we suppose, in this model. I would like to know what's the distribution of z. And the answer is z is distributed as gamma with parameters, with 2 parameters. That's r and lambda, where r is the number of times I'm counting, and lambda is from adding up each random variable. So we're adding up r exponential random variables that are all independent, we get a gamma distribution. Recall that for the Poisson distribution, we add up Poisson distributions, we get another Poisson distribution, but it's not the case that the gamma distribution looks like the PDF for the, so here is the PDF for the exponential distribution. We add up a bunch of these, we get a PDF that looks completely different, and the PDF can look something like this. So for different values of lambda and r, we have something that looks like coming up and then tailing off. Okay. So 2. So this has a real formal PDF, and I'll write that down here. Although it's not so important that you need to know the PDF. F of x here. What's more important is that you know the meaning of a gamma is equal to the sum of independent exponentials with the same parameter. Okay, so f of z, it looks like, again, it's a waiting time, so it can only be a positive number. So for x negative, if x is less than or equal to 0, it must be 0. It's a waiting time. But if x is positive, then it's lambda over r times gamma r, x, r to the minus 1, e to the negative lambda x for x greater than 0. Okay. So this first term here is just a constant. X doesn't appear in it, so it's a constant such that the right-hand side over here will integrate to 1 when we integrate it from 0 to infinity. So because the mean of y1, the exponentials that we're adding up, this is equal to 1 over lambda. So this means that the mean of our z here, which I'm saying is gamma r lambda, and I should make this clear. Here, this is gamma r is equal to 3, and lambda is equal to 2 from what we had before. Okay. So we're adding up 3 of these random variables, or r of them in general, so we get mu z is equal to r over lambda, and the same idea leads us to the variance sigma squared z is equal to r times the variance of exponential random variable. It's 1 over lambda squared, so r over lambda squared.